So maybe we could do a quick mic check for Professor Fuchs. Greetings. Nice to have you here. Maybe we could do a quick mic test and also sharing of your screen.
Uh, I think I'm. How's that?
Yeah, yeah, that's good.
Can
The mic
can
is
you can
good.
hear me well?
Yes, I hear you well. Yes. You could also try to share your screen if you want to.
Okay. And what do you see?
Yes, I see your first title slide. Yes.
Okay, good. What do we see? Okay.
Yeah, thank you.
Okay, so shall I just leave it up or
You can
you want
stop
me
the
to?
sharing and later on you could share it again. Yeah,
Okay.
yeah.
I hope I hope that I can remember what to do. During the pandemic, I gave a lot of Zoom talks and started to oh, I haven't stopped to share. The difficulty is I've forgotten how to do them since.
Mm-hmm.
Well, it's not
There
responding to
should
take.
there should be a stop share, like a red highlighted option somewhere on the screen on your Zoom control. I mean, I could
uh,
also maybe do this for you now. Um, let's see. Okay,
Maybe
I
what
will
I need
start
to do.
in a couple of minutes. So now
What
I
is it
cannot see your
gone?
screen anymore. No, no, now it's gone. You're not sharing
Okay.
anymore. Yeah.
Okay. So I'm in Kolkata.
You are all over India. Yeah.
Has the meeting been going well so far?
It's good. Yes. Yesterday we had two talks. We started from yesterday, and today we'll have two more. So it's like
Okay.
evening sessions every day during the week. So it's
Who spoke yesterday?
yesterday was about Niels Bohr. So like his memories from the archive. So there was one Robert Sunderland, an archivist, I guess, who gave us a quick tour of Niels Bohr's life and all the records and photographs. Then was also Dr. Paula Bohr, who's the granddaughter of Niels Bohr.
Oh, right. I saw that in the list. Interesting.
Yes, yeah. It was more about the Niels Bohr, the person and the scientist kind of
Okay.
session. Yeah. So yes, we'll just start in a couple of minutes. I think the participants are still joining in.
Is there a live audience there or is it only Zoom?
So in Zoom, we have like audience joining in, but I think we're also live in on YouTube.
Oh, on YouTube. Okay.
Yeah.
I didn't appreciate that. So will it be recorded on YouTube and can be found later, or is it just a live thing, not recorded?
This I'm not quite sure, but we can always put it down if you don't like it. So this can be done. But I think, as for my knowledge, I think it's also live streamed. I'm not 100% sure though.
Okay.
Yeah, this is hi Christopher. This is Vasudeva. This is
Oh,
being
hello.
recorded also on YouTube and it will be available on our institute's channel and for live streaming in future if you don't want certain portions that can be also. Or if
Okay.
you don't want to put it, that can be. But for now, it is live. And we have about 135 live participants now. So just for your information, joining from around India and few from outside, also few countries.
So I think we can start now. I will just make like initial announcements, and then I will introduce and invite you for the talk.
Okay.
So yes, good evening, everyone, and welcome back to the Quantum Centenary Lectures, celebrating 100 years of quantum mechanics and 50 years of Bhaktivedanta Institute. And I'm glad to see all of you join us today. We started yesterday, 2nd of June, and these sessions will go until 7th June. We'd like to acknowledge the visionary Dr. T.D. Singh, founder director of Bhaktivedanta Institute, whose mission was to foster harmony between science and spirituality. I'm Dr. Dipankar Sharma, and I am honored to guide you through today's sessions. So this event is organized by Bhaktivedanta Institute, Kolkata, and I'm grateful to have your presence on this journey as we explore today's thought-provoking lectures. We'd like to thank our knowledge partners, Jigyasa Group, Science Consciousness and Inner Quest Group from IIT Bhubaneswar, Soya University Bhubaneswar, Sanskrit University Mathura, Government PG College Ranikhet. Special thanks to International Year of Quantum Science and Technology, IYQ, for promoting our event into the website. Special thanks to CDAC Hyderabad, different IITs, NITs, ISER, NISERs, and many other government colleges across the country. So just a quick reminder for the participants, please, you can find a link in the chat, or you could scan this QR code on your screen to submit your question, which will later be asked to our speaker today. So please, you can already start asking question once we start the lecture, and also after the lecture, which will then be deliberated during the Q&A session. So without any further delay, once I would like to remind you all about the schedule. So yesterday we had two talks, one about quantum spirit, then Niels Bohr, the person and the scientist. Today we have two more, starting with Cubist Descending a Staircase, number 2 from Professor Christopher Fuchs, Department of Physics, University of Massachusetts, Boston, then followed by Plasmas and Cosmic Processes from Dr. Timothy E. Eastman from University of Alaska. Tomorrow we'll have one lecture from Professor David Wallace, University of Pittsburgh. Then on day 4, we have one talk from Dr. Antoine Suarez, Beyond Space and Time. On day 5, we have two more from Professor Anthony Leggett, Nobel laureate in physics. We have one from Dr. Markus Paul Müller, Institute of Quantum Optics and Quantum Information, Vienna, Austria. And on the last concluding day, we have two more lectures from Dr. Wilhelm Bohr, University of Copenhagen, and Dr. Alfred Driessen, University of Twente. So we'll start with the first talk of the day. And to introduce the speaker, I would like to invite Professor Ramji Repaka, Dean of Student Welfare, IIT Dharwad, to kindly introduce the speaker of our next talk.
Yeah. Hi, Professor Fuchs. Welcome to this lecture series. So this is Ramji Repaka. It's my privilege to introduce yourself, your good self. Yeah, next slide, please. So it's a great honor to introduce Professor Christopher A. Fuchs, an internationally recognized scholar in quantum information theory and the foundations of quantum mechanics. He currently serves as Professor of Physics at the University of Massachusetts, Boston, where his research explores deep conceptual questions at the intersection of quantum theory and probability. Professor Fuchs received his PhD in physics from the University of New Mexico in 1996, where he worked under the guidance of Carlton M. Caves, on the topic distinguishability and accessible information in quantum theory. He holds dual bachelor's degree in physics and mathematics with high honors from the University of Texas at Austin, where he conducted research under the legendary physicist John Archibald Wheeler. Following his doctoral work, Professor Fuchs held several esteemed research appointments, including the Lee A. Dugridge Prize postdoctoral fellow at the California Institute of Technology and senior research positions at BBN Technologies, Bell Labs, and the Perimeter Institute for Theoretical Physics. He has authored or co-authored more than 170 scholarly publications with over 19,000 citations, reflecting the depth and influence of his contributions. A standout among them is his co-authored experimental work, Unconditional Quantum Teleportation, which was selected as a top 10 breakthrough of 1998 by Science. Professor Fuchs is best known for founding and advancing quantum Bayesianism or cubism, a distinctive interpretation of quantum mechanics that recasts quantum probabilities as subjective degrees of belief. Sorry for this. For his groundbreaking work, he received the International Quantum Communication Award in 2010 and was elected a Fellow of the American Physical Society in 2012. Most recently, he was named to the 2023 Vox Future Perfect 50, which highlights influential thinkers addressing global challenges. In today's lecture, Professor Fox will guide us through Cubism's ongoing efforts to reformulate quantum theory from a Bayesian perspective, touching upon open mathematical problems and new frontiers in quantum information science. Please join me in warmly welcoming Professor Christopher A. Fox. Yeah, please welcome, Professor. Thank you so much.
No. Well, thank you for
Stage
that
is
very,
yours.
all right. Thank you for that very flattering introduction. I hope that I'm not too technically challenged. I'm going to try to bring my slides up and, and share with you. Well, there goes 5 minutes of the talk. Okay, can you see my slides now?
Yes, please.
Okay, wonderful. Thank you. I've been asked to give a talk on anything that I want, and well, what I always want to talk about is a kind of movement that we call Cubism. I am introducing it with a piece of art by Marcel Duchamp, an early Cubist in the art movement sense. It's titled, the real thing is titled Nude Descending a Staircase, number 2. I have a play on that, and I promise you that I will keep my clothes on for this lecture. Everybody, I guess, gathered here knows that it's the soon going to be the 100th year anniversary of quantum mechanics. This started, or the usual marker for starting quantum mechanics is Werner Heisenberg's trip to Helgoland Island in June of 1925. He had a very bad case of hay fever, and so he went to this island where there were no trees and very little pollen to try to clear it up. And during that time, he had the insight of using a new kind of multiplication rule for calculating things. And he wrote an early paper and gave it to his advisor, Max Born, and in early July. Max Born looked at the paper after he submitted it and realized that what Heisenberg was doing, his new multiplication rule, was just nothing other than matrix multiplication. And Born quickly came across the idea of the canonical commutation relation And really, thus was born quantum mechanics. That paper was submitted by Born and his student Jordan on September 27th, 1925. So maybe that should really mark the 100th year anniversary. But as everyone knows, quantum mechanics is sort of plagued with some troubles. Here's something that David Merman said when quantum mechanics was about 90 years old. Quantum mechanics is the most useful and powerful theory physicists have ever devised. Yet today, nearly 90 years after its formulation, disagreement about the meaning of the theory is stronger than ever. New interpretations appear every year. None ever disappear. So what is cubism? Well, it's just another damned interpretation to add to the list, but it's marked out in a special way in that David Merman himself, by 2014, considered himself a promoter and a believer of the point of view. So I want to tell you about this view, cubism, and really what its goals are. The main goal of it is to be a magic pistol for shooting down all of the various mysteries of quantum mechanics. But in the process of that is meant to be a basis for finding new physics, physics that hasn't been found before. It really took its starting point when I was a student with Carleton Caves, and we were studying the works of a great Bayesian Edwin Janes, E.T. Janes, and we came across a paper that said our present quantum mechanical formalism is a peculiar mixture describing in part laws of nature, in part incomplete human information about nature, all scrambled up together by Heisenberg and Bohr into an omelet that nobody has seen how to unscramble. Yet the unscrambling is a prerequisite for any further advance in basic physical theory. We took that as our inspiration and worked hard at thinking, how might we unscramble the omelet? And the key idea that we got from Janes was that whenever a probability is mentioned in a theory, no matter what the theory, then it should be understood in the Bayesian way, that a probability is not something that's out in nature, but rather something in your head. So if quantum mechanics is talking about probabilities, then it should be that there should be a Bayesian way of understanding those probabilities. And if one can take the Bayesian way and carve it out sufficiently well, then perhaps one can start to see what the real physical content of the theory is. So by 2002, our little group, we were all much younger then, especially me, we wrote our first paper titled Quantum Probabilities as Bayesian Probabilities. That got the ball rolling, but the thing that we didn't appreciate at the time that we wrote the paper was how many flaws and inconsistencies were in it. And we started to realize this slowly, and these were like little holes in the hull of a ship, letting water leak into the ship, and the ship was sinking. In an effort to make the point of view fully consistent, eventually we had to adopt a much more radical form of Bayesianism than Janes himself had adopted. We ended up, one can almost think of the Bayesian movement as a continuous spectrum from a very conservative end to a very liberal end. And where we had to go in order to fix all of the holes in the ship was to take the very liberal point of view promoted by Bruno De Finetti, who famously wrote in the introduction to one of his books this little thing where he says, my thesis paradoxically and a little provocatively, but nonetheless genuinely, is simply this: probability does not exist. He wrote in the center of the page in all capital letters. What he meant by that was, well, of course they exist, people use them, but you shouldn't think of them as factual features of nature. So, whether it's raining or not is a factual feature of nature. The weather report or the weather forecast that it's 75% chance of rain is not a factual feature of nature, according to De Finetti and according to Cubism. Well, it turns out that taking that point of view has profound implications. The key one is this. In quantum mechanics, we always start with a quantum state and then use that entity, that mathematical entity, to calculate a probability from it. But one of the things that we have learned from quantum information theory is that if we consider the probabilities for the outcomes of a sufficiently robust set of measurements, then those probabilities will uniquely determine a quantum state. So it's not only the case that we can calculate probabilities from quantum states, but the mathematics of quantum mechanics, of quantum information, tell us that we can go back the opposite way. So the profound implication was this. We were left with the ghost of De Finetti. My thesis, paradoxically and a little provocatively, but nonetheless genuinely, is simply this: quantum states do not exist. In other words, just like probabilities, quantum states cannot be factual features of nature. That's really the defining feature of Cubism. But I have to tell you, philosophers hate it, absolutely hate it. And it always boils down to essentially this. They start crying, wah, 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 your wave functions aren't real. But they have to be real because my philosophy says so. Well, why would we bring on the anger of so many philosophers? Well, the reason was that if we took this point of view, it had immediate explanatory power. We could explain the no cloning theorem, quantum teleportation, Schrodinger's notion of steering, all of these various things that look great and mysterious actually all arise from the essential idea that a quantum state is not a state of nature, but a state of mind. So it had immediate explanatory power, but it also pushed new physics upon us. We ended up with a theorem that we called the quantum De Finetti theorem. Now, if you look it up on Google Scholar, you'll find hundreds of citations to it. It motivated something called the no broadcasting theorem. The no broadcasting theorem, similarly, is a primitive thing for understanding quantum cryptography, and it's probably near 1,000 citations by now. So it had immediate explanatory power, but it also, in making the point of view consistent, led to new physics, things that wouldn't have been discovered otherwise. Niels Bohr had a nice way of putting it. He said, I felt that philosophers were very odd people who really were lost because they have not the instinct that it is important to learn something and that we must be prepared really to learn something of very great importance. That's the way he viewed quantum mechanics, that with quantum mechanics, we've learned something of very great importance about nature. But it didn't stop there. When one pushes Cubism to the limits, I think we've learned even more than Professor Bohr learned. For instance, Bohr would always depict measurements as these very heavy mechanical devices that were bolted to the lab table. But if one takes Cubism seriously, one finds that one has to give a treatment of measuring devices that is just essentially the same things as quantum states, and just as quantum states are equivalent to probability distributions, and probability distributions are not factual features of nature, measuring devices, the quantum description can be turned into an expression of conditional probabilities, and conditional probabilities, like any probabilities, are not factual features of nature. So among the things that Cubism has eventually led us to understanding, one of them is that the notion of quantum measurement really doesn't fit along the lines of the way Bohr described it. A quantum measurement is any action whatsoever, like for instance, me picking up this coffee cup. This is me taking an action on the world. And its outcome just is the consequent personal experience this induces in the agent. I take an action and it induces some experience for me, tasting coffee, for instance. And that's the consequence. Quantum measurement outcomes are not, to paraphrase Bohr, instances of irreversible amplification objectively recorded for everyone to see in a device whose design is communicable in common language, suitably refined by the terminology of classical physics. It's not that, it's something else. And really, we learned from that that we should probably change the vocabulary for what counts as a measurement. From John Archibald Wheeler, that was mentioned in the introduction to me, we've taken the idea of the participatory universe. Wheeler depicted it this way. He says, quantum mechanics evidences that there is no such thing as a mere observer or register of reality. The observing equipment, the registering device, participates in the defining of reality. In this sense, the universe does not sit out there. So we end up with a picture of the quantum observer that's basically a superhero that takes part in what the world itself is doing. When Captain Cubism takes an action on a physical object, it leads to something new being created in the world. So that's the point of view of Cubism. It's subjective probabilities, and the subjective probabilities are about personal experience. But then you might ask, well, what is the formalism about then? Physicists really want to know about reality. So it should be that the formalism is somehow expressing an aspect of reality. But another thing that Cubism has learned is that it expresses it normatively, not as a fact, but as a should be. So let me try to give you a sense of that by quoting one of the founders of this very subjective Bayesian version, Dennis Lindley. Lindley wrote, De Finiti's paradigm, the topic studied is the situation of an individual who is faced with uncertainty about some events of concern to him. All of us find ourselves in this position. De Finiti's task was first to recognize openly the uncertainty surrounding us. We live in an uncertain world. We've got to recognize that we do, and then see how best we can understand it. The paradigm is egocentric. It is the tale of a single person contemplating the world and not wanting to be stupid. What Lindley was really meaning is that a full-blown development of this idea leads us to decision theory. What probability theory is about really is making better decisions, or as Leonard Savage put it, how to gamble if you must. So let me give you some kind of sense of what it would mean to try to not be stupid. Here's an expression that we find in probability theory. If E and F are mutually exclusive events, probability theory says that P of E or F equals P of E plus P of F. In this subjective Bayesian view of De Finiti, each one of these terms are subjective judgments. It might be that you come to your judgment about the event F from reading one newspaper, and E, you find that you get better opinions from talking to your neighbor. And for this, maybe it's from still a third source, perhaps a third newspaper. And you want to use all of these probabilities for making decisions or making gambles. The normative reading of probability theory is, even though these three entities, these three judgments come from different sources, they had better fit together according to this equation. If they don't, then you're being stupid. In other words, you should rethink the probability assignments that you've made and adjust them ultimately so that they do achieve this equality. Now, that often takes some effort of the will. It's not, again, they're not factual features of nature. So if your probability assignments that you first think up don't fit this equation, then you have to hammer them and beat them into shape until they do fit this equation. So that's what the normative reading is about. But also look what we learn from it. It tells us that not everything is subjective. The individual terms in our equation are subjective, but the equation that they must satisfy is third person. It's invariant, anyone who's using it. It's the norm that is agent independent. Well, cubism views the formal rules of quantum theory as an addition to the book of decision theory. Instead of just simply being how to gamble if you must, what cubism views quantum mechanics about is how to gamble if you must in a participatory universe. And you must. In other words, how to gamble if you take into account that you are like Captain Cubism and that your actions are helping create aspects of the world. This leads us to a mathematical problem. So I told you that cubism is two things. It's about settling the quantum conundrums, or maybe three things, teaching us something about reality, but also as a motivation to invent some new physics. So we want to view the formal rules of quantum theory as an addition to the decision theory book. This gives us the motivation to go to all of the key rules in quantum theory and try to understand them in purely probabilistic terms. For instance, the Born rule for calculating probabilities. We have a probability on the left, but it equals a combination of these abstract operators, Hermitian operators, a quantum state and a measurement operator. Rho is a quantum state, E sub j is a measurement operator. When you look at this, it looks like the terms on the right-hand side are of a logically distinct character from the term on the left-hand side. The left-hand side is a probability, but on the right-hand side, there are these other entities that are not probabilities. They're matrices that involve complex numbers. What we'd like to do is find some different way of thinking about this rule, for instance, but similarly the Schrödinger equation and other equations within quantum mechanics. The key hint comes from Richard Feynman in a 1951 paper titled The Concept of Probability in Quantum Mechanics, where he very quickly says, despite the title of the paper, the concept of probability in quantum mechanics is the same concept that one uses for everything else. And he was a proto-Bayesian himself. He said, the new theory asserts that there are experiments for which the exact outcome is fundamentally unpredictable, and that in these cases one has to be satisfied with computing probabilities of various outcomes. But far more fundamental was the discovery that in nature, the laws of combining probabilities were not those of the classical probability theory of Laplace. So here's what he really pinpointed for us, that what is new and unique in quantum theory is the rule for combining probabilities. So what we take from that is that maybe this, the Born rule, is in a hidden way, a new kind of way of combining probabilities. Well, okay, Feynman had the double slit experiment in mind when he was saying that. And, he has famously said, we choose to examine a phenomenon which has in it the heart of quantum mechanics in reality, it contains the only mystery. So then he goes on to show how one can talk about what happens when you have detectors at the slits versus what happens when you don't have detectors at the slits. You get two different probability distributions. And he says, but actually there is a connection between these two different probability distributions that one can ferret out or one can find by introducing complex amplitudes. So that's all good, and it works mathematically, but Cubism says actually that way of thinking about it distracts from the seminal point that he had made already in 1951, that it's not about introducing new entities like complex amplitudes in quantum theory, with quantum theory, but rather to understand that it's the rules of combining probabilities that is changed. So this led the cubists to attempt to modernize what Feynman had talked about. And this is going to be something that I won't go into as many details as I would like to, but because I don't have the time for that. But I'll just jokingly or tongue-in-cheek, I'll call it the D-squared non-orthogonal slit experiment. Well, really, there are no slits, and so it's and it wouldn't, you wouldn't really know what to do about a non-orthogonal slit. And so let me tell you what it is. It's what is depicted here is a quantum system that is going to be thrown into a first measuring device. This is like going through the slits in the double slit experiment. A measurement will be made there. Potentially a measurement will be made there. If the switch is on, the measurement is made. If the switch is set to off, the measurement is not made. If the switch is on, then the quantum system goes in, a measurement's made, and it reemerges, the quantum system reemerges in some new quantum state that I'm calling sigma sub I here. And then it goes on further to go into another measuring device. So you can think of this as this is like the gun that sent out the electrons back in this picture. And then there was potentially measuring which slit we're going through. And then there's a final measurement at the end. But now I've generalized it. Particularly, I've generalized it in this way. In place of the slits, I'm going to use something that in quantum information theory is called a minimal informationally complete measurement, or a MEC, M-I-C, MEC reference measurement. And in place of the screen at the back, we're going to allow any quantum measurement whatsoever. So it's not just finding the position of the particle on the screen, but any kind of measurement whatsoever. For instance, measuring the momentum or measuring a combination of position and momentum, etc. Notice the way that I've got this depicted. So the quantum state here is depicted as an abstract operator. That's why there is a hat over it. The measurement outcomes of the intermediate measurement have little hats. These are operators. These are sets of operators, and that's why there's hats there. And the measurement outcomes of this other measuring device, again, is a collection of operators, and therefore hats. Under this, you see the P of Ri. What that represents is the probability of outcome Ri. And over here, we could talk about the probability of outcome Ej and the conditional probabilities of Ej versus Ri. Okay, so this is the full diagram. It's got all of the quantum mechanical entities. All of those have hats, and it's got the probabilities that they generate. Now, I want us to do something conceptual. Suppose we take this diagram, and if I could do it with my laser pointer here, suppose I could erase this operator and erase this set of operators and erase this operator. So I'm erasing them out of the picture, and that's depicted here. So now I've got a picture of a measuring device, another measuring device, and I've erased the quantum mechanical origin of all of the probabilities, but I'm still leaving the probabilities in the picture. So I've erased all the details of the quantum business, can we still say how these various probabilities should be related? And the answer is yes. They're related according to something called the law of total probability that comes out of the book of decision theory that I showed earlier. You can give an argument for it called a Dutch book argument that essentially says, unless this relation holds between all of the probabilities depicted here, if this relation doesn't hold, then you're being stupid in some way and you can lose all of your money by bad gambles. I am going to introduce a kind of vector notation now, just so that my next equations can be simpler. Think of the numbers here, P of Ej, as elements in a vector, and think of the conditional probabilities as elements in a matrix. Then what this can be rewritten is vector equals matrix acting on another vector. So this, in essence, is the law of total probability written in vector and matrix notation. Now, I said we get this relation between the probabilities if the switch is on. But what if we turn off the switch? If we turn off the switch, this measuring device basically disappears out of the picture. And what happens is the quantum system goes straight through it, unaffected. And then there's the final measurement outcome at the end. Well, there are no probabilities in this story to connect anymore. There's only the probability of the final measurement outcome. Now we have to use the Born rule to give our guidance. It doesn't appear that we can erase these operators here because they are a crucial piece of the Born rule. We can't erase this operator here. So we don't have a relation between probabilities, or it doesn't look like we do. So you get this dun 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 moment. Actually, if you do a little mathematics, you can re-express the probabilities given by the Born rule in terms of the other probabilities that we had introduced earlier, according to a little equation that looks like this, where we have vector equals matrix times another matrix times a vector. And that new matrix we'll call the Born matrix, and it's defined most easily through the inverse. What it depends upon are these operators Ri and sigma j, which uniquely characterize what this intermediate measuring device is doing. So there we go. The Born rule that started out looking like this actually can be written in terms of probabilities only. This is a completely general statement of the Born rule. It works for any possible measurement. It makes no use of operators or state vectors, and it makes no use of complex numbers. So we now have an expression of quantum mechanics, one of the key equations in quantum mechanics. We have an expression that doesn't use any complex numbers at all. So let me just reemphasize this. The Born rule, born again. This is a formal expression of the Born rule that looks almost exactly like the law of total probability. The difference is in the law of total probability, the extra matrix in here is simply the identity. But in the Born rule, it's something else. It's a matrix that's not equal to the identity. What we see is the expression on the left refers to probabilities in the switch off experiment, and the expression on the right consists of probabilities that refer to the switch on experiment. So these are two different experiments. It's not a contradiction to the law of total probability. So here's what we've learned from quantum mechanics, that the formal rules of quantum mechanics are about how to interrelate probabilities between different experiments. The old Born rule is still semi-visible in this formulation because this probability here is just the probability that we had before, but it turns out that these probabilities represent the measurement operators And this probability distribution represents the quantum state uniquely. So this represents quantum state uniquely. This represents the measurement operators uniquely, but there's this extra matrix. But cubism says, look at this rule and now read it normatively. Recognize that all probabilities are subjective probabilities. And what the Born rule is about is it gives you guidance. It says, if you've come to this probability distribution from the description of your laser that the manufacturer made, and you come to this probability distribution based on the calibration that you've done in the laboratory, and this probability distribution because you've been reading a paper and you think that this is what it ought to be. Those numbers had better fit together according to this equation, or you're being stupid in the sense that Lindley said, stupid against nature. You could lose your shirt when you gamble based on these probabilities if they don't fit this equation. My advisor for the quantum teleportation experiment that we did in 1998, Jeff Kimball, he just recently passed away. He once told me that sometimes you have to put a gun to nature and say to nature, you will do what I want you to do. So this involves the will. So this is the normative reading of the Born rule, but notice what you learn from it. Not everything is subjective. It's the relation, the norm, that is objective, third personal, invariant. And that relation surely is telling us something about a deep aspect of reality. So this leads to a mathematical question that I want to end the talk by telling you a little bit about it. The expression that we've got, the phi matrix, depends upon the particular choice of the meek, the reference measurement in the middle. One would like to modulo that out of the story. The idea is, well, what we have is a deviation. The Born rule represents a deviation from the law of total probability. But we can ask, how big of a deviation is it actually? Well, that will depend upon the reference device. So the question that we'd like to ask is, what measurement device will minimize the distinction between these two entities? In a sense, that expresses conceptually Cubism's version of H bar. It says this represents the minimal engagement that an observer always has, that an agent always has when they act on a quantum system. So that's a mathematical question. And you can quantify it, for instance, by saying, oh, these are two matrices. Let me take the distance between the two matrices and find the phi matrix that minimizes the distance between this one and that one. And you can, for instance, introduce matrix norms. There is a very large class of matrix norms called the unitarily invariant norms. And you can say, well, let me minimize the norm distance between these two matrices over all reference measuring devices and see how small it can be. Well, it turns out that you can find a lower bound to it. And the secret ingredient for getting a lower bound to that distance introduces this mathematical concept, something that I'm going to call a seek. So we had minimal informationally complete measurements. Now let me talk about symmetric informationally complete measurements, or seeks. We can think of these as measurements or operators or quantum states. Here's the key ingredient. For any Hilbert space, for any quantum system of dimension d, we need to find d squared, not d, but d squared projection operators that satisfy a very beautiful and simple symmetry. Namely, that if we take the inner product, the Hilbert-Schmidt inner product, between any two of the ones up here, we always just get a constant number. Or if you want to think in terms of state vectors, what we get is that the inner product of any two of these state vectors is just this constant value up to a phase factor. If such a set of operators exist, then we can achieve the lower bound of the distance between so the distance between this and this is lower bounded by a certain quantity if for all reference measurements, if we can find a set of operators that satisfy this beautiful little symmetry, then we can achieve equality in the lower bound. And when we do that, we see really a stark expression of the difference between the classical equation, classical law of total probability here, and what the Born rule looks like when expressed in terms of the secret ingredient. It's just a very minor change. What happens is that this term P of R gets modified to D plus 1, the dimension plus 1 times P of R, and we subtract a little bit. But that difference makes all of the difference in understanding reality. It explains everything that we have seen in quantum mechanics, because everything that we see in quantum mechanics is a result of using the Born rule. Similarly, the Schrödinger equation, if you work through the Schrödinger equation, you can find a way of expressing the Schrödinger equation in exactly this kind of form. All it takes is that we have this secret ingredient to be able to use for the reference measurement. But here's a mathematical question. Do these seeks exist? Well, the question of their existence was first posed in 1999 when Caves, Schock, and I were working on the quantum Diffinetti theorem, and independently by Gerhard Zauner in Austria, 1999. And we could see that it ended up that we didn't need the seeks in order to prove the quantum Diffinetti theorem, but the question was still there. Can you find a measurement of this variety? And that was long before actually that we knew that if such a measurement existed, the Born rule would take this very, very simple thing. In 2017, in the background here, I have a little bit of it. In 2017, a student and my postdoc, Blake Stacy, and I wrote a review article about the state of play of trying to prove whether these things exist. And here's what's currently known. What's currently known is that there is numerical evidence to very, very high precision, even to thousands of digits, that they do always exist in all dimensions up to 193, and then in some sparse dimensions where there are special symmetries that one can use. What we know now is, so that's numerical evidence, but actually analytical proofs have been given in all dimensions less than 53, dimension 57, dimension 61, etc. You see the full list here. We have come a long way in exact solutions since the 2017 review paper. Much of this is due to Marcus Grossel, who has really unlocked a lot of information about the structures. And maybe this slide is a little too busy, but there are other dimensions where you have an exact proof depending upon a certain conjecture in number theory. So after 26 years, no one still knows whether the secret ingredient for getting the essential quantumness exists after all. A formal proof hasn't been given in all dimensions. And a few years ago, about 5 years ago, it became clear why no formal proof had been found before. There was a shocking discovery that proving that seeks exist in all finite dimensions appears to be deeply connected to one of Hilbert's 23 problems that he offered at the turn of the last century. This is problem number 12. It has to do with algebraic number theory. And that problem, just to tell you just the bare bones of it, consider the unit circle in the complex plane. Here I've depicted the seventh roots of unity. Okay, these are the seventh roots of unity. If you look at their coordinates, then you find that the expressions for the roots of unity can be constructed by taking roots of roots of roots. So there's an expression in terms of roots. But there's also a transcendental function, the exponential function, that gives you a very simple way of expressing the roots of unity. So you can either express it in this complicated way, or you can express the roots of unity, the first root of unity, in this very simple way by making use of a transcendental function. What Hilbert's 12th problem is about is whether one can always do that for every algebraic number field. There we go. So we can ask, why would the representation of the Born rule, exhibiting its essential quantumness, care about Hilbert's 12th problem? So if one could find the analog of this exponential function for the certain algebraic number field that the seek problem suggests for its solution, then one would have much of the proof of seek existence. But why would the Born rule, why would the mathematical structure of the Born rule care about that? Well, I can tell you that most of the philosophers that I meet at philosophy of science meetings wouldn't care. They would still be hung on the idea, you don't believe wave functions are real. They have to be real, and they don't listen to anything else about cubism beyond that. But a physicist might smell that there's an opportunity to, quote Bohr, learn something of very great importance from this. So I hope I've given you an introduction to the philosophical aspects of cubism, but I hope I have also given you some introduction to the kind of live mathematics that cubism suggests to us and gives us something to do for those times when we feel like shutting up and calculating. You do that for a while, but if we ever solve this problem of the seek existence, I think we're going to learn, we will uncover a new kind of diamond that's buried within quantum theory. So that's all I've got for you. Thank you. Thank you for your attention.
Thank you, Professor Fuchs. This was a fascinating and a very foundational talk. I really appreciate. So I would like to request the participants to post their questions, which then I will read out to Professor Fuchs. Meanwhile, maybe I can start with a question of my own. As someone trained as an experimental quantum physicist myself, I'm curious about the practical reach of cubism. Are there any directions, let's say something experimental or technological, where cubism leads to a different prediction compared to the other interpretations?
Oh, that's a very good question. Let's take the seek existence question. Cubism was the first to even suggest that one look for these things. I want to share screen again and show you a slide from a different presentation, if I can get there. Where did it go? Oh, it's not in that one. Let's see. Give me one more second. I apologize.
No problem.
Give me 2 seconds. Let's try this one. Oh, I will be darned. Okay, I give up trying to find the slide. I wish I had included in it. If I had only known that your question was coming, I would have included the slide in my talk. Um, Short answer is yes. We expect Cubism to make quite an impact on physics. The Sikhs, for instance, I wish I had the slide. It would be so much more effective. Um, um, it turns out that these Sikhs are optimal measurements for quantum tomography. So you, as an experimentalist, if you want to build the best device you can for revealing what quantum state is being prepared under the assumption that there's a uniform distribution of quantum states, and you want to make the least number of measurements possible, then the device you should build is one of these seeks. If you want to generate optimally secure random numbers, then the seeks are the optimal solution for that. They're also optimal for entanglement detection. Most recently, we put a paper on the archive, a student and I, proving that with regard to a kind of quantum computation called Clifford group computation. This is a method of doing quantum computing where you only use Clifford gates because they're easy to build. But the way to get the computation universal is to inject into a circuit something called a magic state.
Mhm.
It turns out that the Sikhs have maximal magic.
Okay.
This can be proven. So in a sense, you get the maximal speed up in a Clifford gate computation by injecting them with these kinds of states. So that's some of the experimental
Mhm.
implications. People have done proof of existence experiments in dimension 2 and in dimension 3 for the Sikhs, and I'm working with a group in Japan. Hopefully, we will see a dimension 4 Sikh come out of an actual demonstration. So I hope that answers it a little bit. I wish I
Yeah,
could have shown you this.
it does. Thank you. Maybe I can ask Ritvik to put up the question next. Yes, thank you. So it's a question from Yogesh Tambe. He says, is wave function objective or subjective?
Well, you're going to have several talks. One of them is by David Wallace, and David Wallace is going to tell you that a quantum state is objective. And my version of that is basically David is saying, wah, 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 they have to be objective because that's the only way to understand them. But the basis of cubism is that wave functions are subjective. If you want to know a quantum, so if you can see it already in the no cloning theorem. If I hand you a quantum system and I give it to you and I say, I have a quantum state for that system. Examine the quantum system in every way you wish. You can't find out what quantum state I have assigned to it. There's no physical measurement. That can be proven, and it's equivalent to the no cloning theorem. If you want to know the quantum state that I have for that system, you have to ask me. So in that sense, it's subjective. And a different observer, a different agent may have a different quantum state for that. And the
Mhm.
quantum states reflect their probabilities for various measurement outcomes, their degrees of belief. So a quantum state now is a collection of degrees of belief in cubism.
Okay, thank you. So the next question is from Nikhil Kumar Shah Sahu. It's a quite long question. He says, Decade-long experiments like the quantum eraser and delayed choice setups have discredited the older speculations about consciousness playing a decisive role in quantum phenomena. For instance, Yu's paper titled Quantum Mechanics Need No Consciousness presents strong evidence that the collapse of wave function is governed purely by physical interactions, without the need of any conscious observer. An irreversible physical measurement or record appears sufficient to resolve superposition into definite outcomes. Okay, the question is, in light of these findings, does consciousness still hold any actual relevance or theoretical space within the quantum physics today, or has it been quietly evicted by the physics itself? Thank you
Yes.
for it. Yeah, that's a
Yeah,
nice question.
just as with the last question, it's going to depend upon who you talk to. If you talk to Roger Penrose, he would say, no, consciousness is absolutely important for things. Um, y- I would say cubism itself doesn't have any use for the word consciousness in it. It reimagines what quantum theory is. Quantum theory is a decision theory. It helps you make better decisions. What does it take to be an entity that makes decisions? Well, if you look at the decision theory book and the one that I like showing, the one from Leonard Savage, if you read the introduction, it says, who can be a user of this book? It doesn't ask, must the user of this book be conscious? So in that sense, I don't think consciousness plays any role in understanding what quantum theory is. On the other hand, it is important for cubism that what the theory is referring to, what it's about, is how we make decisions based on what we do in the world. And
Mhm,
whatever it is, I mean, maybe an AI can do that, or they can't yet, but maybe eventually they will. But that's what the subject matter is as far as cubism is concerned.
mhm. Yeah, thank you. I think, as you mentioned, the AI, the next question, I think it's in the similar line, what Dr. Bharat Pandey is saying in today's rapidly evolving quantum world, where AI, quantum computing, and human perception increasingly intertwine, if we imagine the cubist observer as a conscious agent descending a staircase of quantum experience, each step revealing a new subjective update of belief, then how should we rethink the role of agency in shaping the very fabric of scientific knowledge?
Oh gosh. Uh, no, leave that question up. I've got to absorb it. I think that's
Yeah.
probably a very deep question and one that I won't be able to answer so quickly. Um, if we imagine the cubist observer as a conscious agent descending a staircase of quantum experiences, each step revealing a new subjective update of beliefs, then how should we rethink the role of agency in shaping the very fabric of scientific knowledge? Yeah, the slide of David Merman from his Nature article of 2014, when he had his epiphany and he had his epiphany in 2012 and wrote the 2014 article for Nature titled "Cubism Puts the Scientist Back into Science."
Mhm,
Um, I surely feel deep in my bones that there's some insight to be learned from this, that we have discounted the role of agency in the world. We think of ourselves as insignificant little nothings. And what this uh, view of quantum theory helps us understand is that we're not insignificant nothings. But now, by we, it might be a broader concept than whatever I can put into a human brain. We might include big data centers if they can start acting autonomously. But I,
mhm,
I don't feel I can answer the question better at the moment. I would encourage the questioner to read a couple of my papers where I at least attempt to make a broader statement. One of them is titled Notwithstanding Bohr, the notwithstanding Bohr, the reasons for cubism. Notwithstanding Bohr, the reasons for cubism is the title of the paper. And at the end of that, I think I address a little bit more of what's being asked.
Thank you. We have many questions. Maybe we can take one last question for today. So it's from Vasudevaji. He's asking why combining quantum probabilities have to be different if they are really, after all, probabilities. Does it have any consequences to probability theory?
No, I don't think it has consequences for probability theory itself, because I think that probability theory is something that is defined a priori without reference to what particular world we live in. But what the probabilities in quantum theory refer to are not objective states of affairs, but what will come about by measurement actions. And what the distinct rule for combining probabilities is about comparing not taking an action to taking an action. And that's where you get a modification of how the probabilities should be combined. So it's true, the probabilities remain subjective, but what we learn is that if you ask the question, probability of what? It's the what that has changed profoundly. One used to think that probabilities were probabilities of objective states of affairs. And in quantum mechanics, we learn, no, my probabilities are about what arises from my actions. So that's what changes. Probability doesn't change. Probability of what? The what changes drastically.
Yeah. Okay. Thank you. Thank you so much. I think this was wonderful listening to your talk. For me, it was like a new perspective of looking at quantum theory. Thank you so much for this wonderful talk, and we really appreciate your presence and taking your time out to deliver your lecture. Thank you so much.
Well, thank you all for having me.
Thank you.
I hope you have a great conference for the rest of it.
Thank you so much. Nice to have you. So we will now proceed with the second talk of the evening today from Dr. Timothy E. Eastman, which is titled Actuality and Possibility, Space Plasmas to Quantum Physics. Again, quick reminder to all our participants, please click the link on the chat or scan the QR code on the screen to pose your questions, which we will then ask to the speaker later on. So moving on, I would like to invite Dr. Pawan Kumar Chamling, Department of Civil Engineering, NIT Andhra Pradesh, to kindly introduce the speaker of our next talk. Pawan Kumar, if...
Yes, thank you very much, Dr. Deepankar Sharma. Now we will introduce to Dr. Timothy E. Eastman. Formerly, he was associated with Geophysical Institute, University of Alaska, USA. So it is a privilege to introduce Dr. Timothy E. Eastman, a highly respected scientist and philosopher whose interdisciplinary work span the field of space physics, plasma science, and philosophy of science. Dr. Eastman earned his PhD in physics and geophysics from the Geophysical Institute of the University of Alaska in 1979, where he conducted pioneering research on Earth's magnetosphere. Notably, he discovered the low latitude boundary layer in 1975, a key contribution to our understanding of solar wind magnetosphere interaction. Over the course of his career, Dr. Eastman has published more than 100 scholarly articles across space physics, plasma, yes, space physics, plasma thing, and philosophy. He has served in key administrative and research roles, including as a programmer officer at NASA between 1985 to 1988, and the National Science Foundation 1991 to 1994. In this capacity, he co-developed foundational framework for major interdisciplinary initiatives such as the International Solar Terrestrial Physics Program, the Interagency Space Weather Program, and NSF Basic Plasma Science and Engineering Program. Dr. Eastman's scholarly engagement with the philosophy span more than 4 decades. He is the lead editor of two important interdisciplinary volumes, Physics and Whitehead, Quantum Process and Experience, published by Sunny Press in 2004, and Physics and Speculative Philosophy in 2016. In 2009, he was honored with the Creative Advance Award by the International Process Network in recognition of his research bridging science and philosophy. His most recent work, Untying the Gordian Knot, Process, Reality and Context, published recently 2020, outlines the integrative logi framework and interdisciplinary approach that draws on development of physics, logic, semiotics, and process philosophy to explore questions on natural philosophy. Dr. Eastman also founded and maintains the educational resource website plasmas.org dedicated to plasma science and its wide-ranging application. Please join me in warmly welcoming Dr. Timothy E. Eastman. Now, all over to you, Dr. Eastman. Yes.
Hello.
Yes, I think you can share your slides and we could start.
Okay. I'm looking into how to share the slides.
There's a share option right on your screen. You could just click there and choose the already opened slides.
I'm looking for that. Yes.
Or
Okay. Okay, on share.
yes. Do you have a PowerPoint or a PDF? Then you could,
I have a PDF.
yeah, once you click on the share, you could choose that PDF which is already opened and maybe start sharing.
Under advanced pairing options.
There would be like windows popping up and you select the one with your PDF. Or we could also share it for you. I think we also have the presentation.
Yeah, Tim, if you have a difficulty, we'll share from our side.
Yes.
Perhaps do that. I don't quite see why.
So we
Okay,
have
it's here
up
now.
now. You can see on the screen that we shared your presentation.
Okay, that is fine.
Yeah.
Okay, are we then ready to begin?
Yes.
Yes, Tim, you can go ahead.
Yes.
Okay, well, thank you for the opportunity to present this material about plasmas and cosmic process. Uh, I um, I hope now that you can see the presentation okay. Uh,
Yes.
Okay, yes. This is based especially on uh, two works that are on the list, on tying the Gordian knot, which was just mentioned in the introduction, which came out in 2020, and more recently, a essay published by Perry Perspectives in January 2025 titled Orders of Possibility and Actuality. And so the Untying the Gordian Knot includes within it a very extensive critique of mechanistic philosophic approaches or also and scientism, which I recommend to you for that kind of focus, in addition to its effort towards working towards a new natural philosophy. Next slide, please. So I'd like to dedicate my presentation to Professor Giant Nailekar, who just passed away only 2 weeks ago. I very much appreciated and greatly benefited by his great work with Fred Hoyle and others. He was an outstanding physicist, always humble. He consistently explored alternatives to his works in cosmology and astrophysics. He always checked his own steady state model with observations, and he's always had the deep intuition that the universe was not really of simply 13.8 billion years of age and some kind of finite span like that, but was really of an indefinite time scale, which I will come to. That my argument is that his intuition was likely quite correct. Next slide. So my key points to this presentation are that the Big Bang Research Program, which itself as a program is not falsifiable as such, sort of in the sense of the philosopher of science Imre Lakatos, but its specific quantitative models, such as the lambda CDM model in particular, which is sometimes referred to as the standard Big Bang model. That specific predictions of it quite recently have very definitively failed, and that there's an alternative model that does succeed. There's, of course, many cosmology models these days. There's well over 30 such models, and it's been presumed that the Big Bang model, the lambda CDM model, is the preferred one, with high confirmation. Well, this was roughly the case up until about 20 years ago, but over the last 20 years, it's increasingly been challenged, and especially in the last few years with the Hubble results and the James Webb Space Telescope results. So the results I interpret from all of these new developments is that the universe really is of indefinite age, as Professor Nailekar suggested for us, perhaps trillions of years or more, and that both gravity and electromagnetism, electricity and magnetic effects, and plasmas, understanding these and working with such concepts are required for contemporary cosmology, not just to focus on gravity. That a key breakthrough has come recently with regard to understanding redshift. That's a key element for understanding these, interpreting the data from recent quantum spectroscopy research, which I'll make reference to, that we have actually observed filamentary or vortex structures of space plasmas at all scales. And then turning now with a focus on the philosophic side, that I will introduce to you a new non-reductive natural philosophy for the 21st century that makes a distinction of a fundamental order of actuality and of possibility. And so next slide. So this natural philosophy I point to and develop in some detail in my work on tying the Gordian knot from 2020, weaves quantum physics triads of input-output context, fundamental logic, complex systems theory, semiotics or the theory of signs, and process relational philosophy to demonstrate how potential relations, both local and local global, can provide a grounding for causation, emergence, and physical relations, that is, quote, laws. Its ways of knowing incorporates both context emphasis, as in Hearts and the Humanities, and context independence, that is, the emphasis in scientific representation, and argues for the inevitable role of ultimate context, that is, meaning and the spiritual dimension, as part of a transformative ecological vision. Next slide. So this logoi framework, or it's basically a relational framework, using the Greek term logoi as a way of labeling this, that the most fundamentally should be considered as both the actual space-time particular given the hard whatevers of the world, the actualized things, the actual plus ontic possibility, possible relations, or possibilia. And that to consider laws not somehow as God-given things, but as physical relations that arise as a result of constraints and possibility, which is indicated through the principle of least action and other ways of deriving some basic physical relations. And I argue that they're fundamental ontic levels, that they're both epistemic and ontic considerations. In the previous presentation, some very scholarly work was done to focus on epistemic aspects of systems. But here I wish to argue that there's both epistemic and ontic, and that in fundamental ontic levels arguably are a quantum substratum or pre-space, a veiled reality, as well as an actualized time-space quantum world, the experiential now. That experiential now being and as a subset of that experiential now, classical models provide a modeling, a representation that's very powerful applications, but are only approximations, never a basis for fundamental ontology. Next slide. So at the foundational level, I would argue that we need to have, and this several people have argued this case, especially Hans Primus, Michael Epperson and Ilya Safiris, Ruth Kastner, Gordon Kaufman, and others, that we, at the most fundamental level, need a logic of actualization, or what's called a Boolean logic, after George Boole, mid-19th century mathematician, in which there's only two values, either true or false, either things are 1 or 0, on or off, in which you don't have an in-between. That is an excluded middle logic. And you need a logic of potential relations, or potentia, a non-Boolean logic or free logic that enables the possibility of maybes or the in-between. Quantum physics arguably requires both a logic of actualization and a logic of potentia, unless one insists on actualism and appeals to multiverses. Next slide. As well, I would argue that quantum process is fundamentally triadic, that fundamental logic, philosophy, and human experience, quote, mirror the general evolution of quantum states from actual potential states, rife with quantum superposition, to a return to actualization. Modeling this fully involves triadic structures, including logic of both potentia and actualization, always the triadic of input-output context, not just a simplistic input-output dyad. This is brought out in some detail in a work I did with philosopher George Shields on the topic Triads as Primal, published in Process Study Supplement, which is available online from 2023. Next slide. So a summary of the logoi framework that I bring out in my work on tying the Gordian knot in some detail at the top level are the notion of process, that is input, fundamental quantum process, input-output succession within context, constraints and potentia. Logic considerations I've already referred to, a logic of actualizations and a logic of potential relations, including potentia with multi-valued logics, and also relations at a most fundamental level, constitutive of process, both considerations of part whole, local global, internal external, and relations of relations, and that is semiotics, the theory of signs, extension, and relations in category theory, a major aspect of mathematics, considering mathematics fundamentally as theories of relation. Thus, we have two fundamental onic levels, a veiled deep pre-space reality and our experiential now, that is actualized space-time quantum events. And with this, we can look anew at considering a broader mind space and understanding of consciousness whereby the brain acts as a filter and that consciousness somehow isn't just merely brain states, but that the brain is part of a broader mind space, and consider anew how minds can tap into potentia, achieving in however limited a way some connection with ultimacy, meaning, and value. Next slide. So from here we've focused on quantum process so far, so let's transition to the space plasma environment, the nearby astrophysical environment, onto broader astrophysical and also finally cosmological issues. Key to this point is a development, quite recent development, that has shown, as Andreas Schlatter and Ruth Kastner have shown, that Einstein's gravity physics can be derived from quantum field theory, and thus is not equally fundamental to quantum physics, as presupposed in many efforts to work towards a united theory of the fundamental field. That effort towards a unified field theory throughout much of the 20th century simply presupposed that quantum physics and relativity theory were at equal level. This result instead argues that the relativity is actually derivatives. Further, in contrast to the Big Bang research program, in which multiple hypothesized entities, that is dark matter, dark energy, inflation, black holes, have evaded observational test or confirmation for decades, I will outline here a new gravity plus plasma model that requires no new physics, that can explain basically all cosmological observations to date, including the most recent observations representing exceptional challenges to the popular Big Bang model, such as direct detection of galaxies at the very limits of observation, at the very limits of redshift, that are fully formed, that had to have evolved at least a couple billion years, which then pushes the timescale well beyond the standard Big Bang limit of some 14 billion years. Next slide. So getting back to some fundamentals about primary natural systems, we often in school and high school learn about solids, liquids, and gases. And this is all in terms of neutral states, solid being the more compact, hard kinds of conditions of things, fluid being expansive, whether in the form of neutral gases or fluids in a normal manner. But also there is plasmas, which arguably is either a third state or a fourth state, depending upon how you consider it. If you think in terms of solids, liquids, and gases, then plasmas represent a fourth state of matter in terms of naturally occurring, common naturally occurring state. Of course, there's other exotic states, over 30 plus exotic states, but in terms of common naturally occurring states of matter, there's basically the solids, liquids, gases, and plasmas. But I'd also like to think in terms of systems, that there's condensed matter systems, fluid systems, which can be represented by what's called the Navier-Stokes or fluid theoretical framework, and electromagnetic systems, where you have to bring in the Maxwell-Boltzmann relation and the Maxwell equations to help describe such systems. So in terms of systems, we really have these three. Next slide. So space plasma physics is an area that has been my area of specialty throughout the 1970s through my retirement this past decade. And they're multi-scale, from laboratories to solar system to galaxy and beyond. And they're basically, in certain aspects of them, are scale-free. That is, they provide exemplars at each one of these scales. Goldblatt and Potts, who published Principles of Minute Hydrodynamics, the major aspect of plasma physics, from Cambridge Press 2004, they state, the nonlinear interaction of plasma and complex magnetic structures presents itself as an important common theme of lab and astrophysical plasma research. Large-scale tubular magnetic structures occur that move with the plasma so that magnetic forces are transmitted with the fluid. One could hardly imagine a larger contrast with central electrostatic and gravitational forces decaying in vacuum with distance as 1 over r squared. So there's aspects of plasma physics that are dynamically important that are neglected by just setting aside and focusing on gravity alone or a central force approach. Next slide. So in the plasma universe, so we have, so to speak, there's the visible and the not so visible universe. And the plasma universe, so to speak, both of these stars and everything we see, essentially all the emitters as we look out, uh, emitters of the photons themselves are most often a plasma source. And as we look at the sun, we see the sun, and the sun emits a broad range of energies and peaks in the visible spectrum, and our eyes have evolved and adapted to take advantage of that peak in the visible spectrum. But there's shorter wavelength in the ultraviolet and X-ray. There's longer wavelengths in the infrared. And here's a picture of a prominence of the sun taken by spacecraft in the ultraviolet, exhibiting the plasma universe. Next slide. And the sun, if you see it in, say, both the ultraviolet in this central disk, uh, which shows various prominences, but superimpose an X-ray photograph of a coronal mass ejection, a CME, you can see this dramatic CME coming out from the sun to the right-hand side here, along with all of the outflow of feeding the solar wind that you see in all directions around the sun. And this feeding of the solar wind is always going on. You only once in a while have the kind of solar storms or solar flares or coronal mass ejection that you see in this dramatic case. Next slide. Now, as the outflow from the sun goes out in supersonic speeds in every direction, this plasma outflow, then you have interaction with various obstacles, with moons and planets. And here we have an artist depiction of how the Earth is embedded in the upper center of this artist illustration, and how the Earth's magnetosphere forms with a shock wave out in front of the Earth, and then you have a blowback of this magnetic or plasma environment to a long magnetotail, and the Earth's radiation belt and the inner environs, and you can see the Earth depicted as a small blue dot in the middle of that. But Earth is effectively a great comet if you could actually see its full magnetosphere. And indeed, every obstacle in the solar wind flow is effectively a great comet, so to speak. Next slide. And thinking about plasma's characteristics and in their space plasma implementation, that they're multi-scale, a variety of scales in density and temperature and scale length. There's filamentary, there's directionality, there's connectivity and interactivity. And in 4 successive slides, I'll illustrate this. Next slide, please. So here's the way in which multi-scale from here in number density per cubic meter from 10 to the third to 10 to the 33rd, tremendous scale in number density, tremendous scale in temperature. This illustrates particular examples from very tenuous space plasma and auroral features to the very high densities needed for fusion, as in the center of stars and in fusion experimentation. Next slide. And filamentation is illustrated by the aurora at both the northern and southern polar cap that are dramatic signatures of the plasma environment from the ionosphere, magnetosphere on out. Next slide. And then the directionality exhibited by the lightning that we all experience at times during dramatic Earth-based tropospheric storms. Next slide. And then how it conducts electricity. Here's a plasma experiment in Albuquerque, New Mexico, that at one point really dramatically showed the visible forms of conduction at very high current. Next slide. And then interactivity. Here, another illustration of the Earth and its geomagnetic field with the inner field displayed in the red and the yellow, and then the blue and green illustrated the outer ring current and magnetosphere with the solar wind approach and sun from the right-hand side blowing back to magnetotail on the left-hand side. Next slide. So with cosmology and astrophysics have traditionally focused on neutral bodies and gravity, which is reasonable as a first approximation. However, the approximation of plasmas as fully shielded ionized gas, implicit in simplistic references to gas and not to plasmas, is invalid everywhere direct measurements have been made, where we've taken spacecraft with plasma magnetic field measurements near Earth and indeed to the outer planets and throughout the solar system and done direct in situ measurement. The approximation uh, that that uh, that the plasma effects can be fully shielded out is just simply not the case. There are two long-range forces of relevance at astrophysical scale, both gravity and electromagnetism. Next slide. So the limitations of modern cosmology is that we lack a unified field theory. We don't really understand how gravity and quantum theory relate. And then, as I noted more recently, it looks like gravity is derivative from the fundamental quantum field theory. And further, cosmology is intrinsically an historical science and lacks direct experimental testing. You can't replicate it and repeat it as you can in a laboratory. And data in cosmology are in general limited to remotely sensed photons. There are no direct in situ measurements, that is, in place, right in the place, as possible in solar system, space physics, or planetary science. And most existing cosmology models focus on only one long-range force field, gravity, and ignore effects of plasmas and electromagnetism, assuming incorrectly that such effects are 100% shielded out. They are, mind you, substantially shielded out, like 1 in 10 to the fifth, 1 in 10,000, 1 in 100,000, but they're not 100% shielded out. And the fact that they're not 100% shielded out has major impact. This is developed in some detail at cosmology.info, the cosmology group. Next slide. So one particular test, and there's multiple tests like this. This is an example that's dramatic with respect to the predictions of the Big Bang, specific quantitative Big Bang model of how the surface brightness of galaxies, it's called a Tolman test. And this, and the prediction of it gives rise to this red line. That's the specific quantitative prediction of the standard lambda CDM Big Bang model as currently represented, in contrast to a sets of measurements that I assisted Eric Lerner beginning around 2005 when I worked at NASA Goddard Space Flight Center, working with the National Space Science Data Center there as a group manager. I helped him gain access to galactic data to do this surface brightness test. And then he's followed up with multiple checks over the last 20 years, most recently with a paper about 2 years ago, that ever more provides data to test this model. And here are the data points in this slide. And the data points map right around the result that the surface brightness is a constant at all redshifts, right up to very high redshift. And redshift is a change of wavelength of the photons as emitted by a source, and that roughly are scaled. So it's so the prediction of the Big Bang model is specifically falsified and a versus a non-expansion prediction. Next slide. Now, Lerner's galactic origin of light elements model, which I find most promising, is that it explains all basic observations without inflation, dark matter, or dark energy. We don't need these hypotheses. That all the light elements are created, as well as the heavier elements, are created by thermonuclear and cosmic ray processes in young galaxies, as confirmed by observations. The Big Bang predictions appear to be contradicted by a large number of data sets, whereas this model of Lerner's appears to be supported and not contradicted by any, but there are specific predictions in advance of the James Webb Space Telescope data that there would be fully formed galaxies at the very limits of observation. And that prediction turned out to be the case in contradiction to the lambda CDM model, which specifically predicted that you wouldn't have such galaxies. And but, however, that model requires a non-expansion redshift, in contrast to most cosmological models, which requires expansion redshift. So that was a limitation because we didn't have such a redshift. Next slide. However, recent results have shown, well, indeed, Narlikar in his paper with Burbage 2008, in our view today, the most basic question to be answered is, do we really understand the nature of the redshift? This is the very last line of that book. It was emphasized by him. And sure enough, it turns out that the redshift, not having it correct, is a major issue. However, quantum spectroscopy lab research recently has revealed the spectral transfer redshift providing coherent and non-blurred redshift based on modern quantum electrodynamics. And the predicted redshift via tenuous electron space plasmas, as expected, however, will require, the direct testing will require significant improvements beyond the current technology. Next slide. However, with this redshift, both gravity and electromagnetism is then expected at all scales. And Eric Lerner calculates that a recently observed big ring of galaxies interpreted as a rotating electromagnetic plasma helix system using his 1986 model would be expected to have a radius of 1.2 billion light years versus about 1.1 billion light years as observed. So this is most interesting, a prediction in a paper some time ago that then these recent observations confirming it. And these observations are of a ring. You can see in this display, it's the blue circle, a set of galaxies, a pattern, a clear ring, and at the at the, at the speed scale of typical, roughly the limit uh, of astrophysical dynamic movement on the order of 1,000 kilometers per second. In 14 billion years, in the nominal scale of the Big Bang, you'd only achieve a distance that's a fraction of the diameter of this big ring. In order for that ring to be created, it would require tens of billions of years at the minimum. Further, it illustrates the inhomogeneity of real systems at such scale. Next slide. So when you take and look at with the most sophisticated recent telescopes, including the Hubble and James Webb Space Telescope, when you look at a region that appears to be completely dark and without anything, and you focus on that and do a long time exposure with the very best resolution, it turns out that this is the kind of thing that you see. You see galaxies without limit. You see clumping without limit at all cosmic scales. Of which in these inhomogeneities, the Big Ring is just the latest example. The result here that we're seeing is that the so-called cosmological principle, in which you insist on homogeneity and isotropy at the largest scale, as required to solve the Einstein general theory of relativity and apply it to the cosmology problem, is simply not the case. So therefore, you cannot properly apply Einstein's general theory of relativity to cosmology as presupposed in the Big Bang research program. So this real homogeneity, such clumping, is what the real cosmos gives us, not the idealized homogeneous concept of artificial models. Next slide. So force-free magnetic vortices are predicted in the space plasma domain and are directly observed throughout the solar system and beyond. This comes right from the pinch effect in space plasmas that inevitably occur at multiple scale. Indeed, arguably, it's been directly seen in stellar and galactic scale, as shown by this example of the Vela Nebula, and expected, because of scale free, to be true at all scales. So the combination of both electromagnetism and plasma effects and gravity in combination can create over billions to trillions of years a hierarchy of filamentary structures, in turn creating superclusters, clusters, galaxies, stars, planets. And in the long term, this process represents an evolutionary building up of the cosmos, not a running down. Next slide. So this illustrates all these scales from a different scale, but and this in log duration in years. So from millions to trillions to millions to billions to trillions of years at the longest scale here, as expected in the sequence of model of scale-free effects in Lerner's model. Next slide. Thus, I would argue that there's really consideration of deep time and possibility, and quoting Narlik and Burbage in their work of 2008, Facts and Speculation in Cosmology, quoting, "The day or night of Brahma, the creator of the universe, is equivalent to 4.3 billion human years, 4.3 trillion human years. The thinkers of the day did think of timescales far in excess of normal human lifespan." And then further, quote, "Our fundamental ontology now incorporates both an order of actuality and order of possibility," as I argue in my work in Orders of Possibility and Actuality. "The former evinces radical diversity. The latter's possibility amplifies diversity, and yet for such ultimacy in potentia requires a grounding, perhaps a kind of unity suggested by arguments for the absolutely necessary dimension of being, or Brahma." And with that, I'll close and be open for questions. Thank you.
Thank you. Thank you so much for your very nice, inspiring and integrative lecture, Dr. Eastman. It was really interesting to listen the content of this lecture. So we'll start with the Q&A. Maybe I can ask Shravan to put up some questions so that you can also read through them while I ask. So maybe I start with asking that you describe a new natural philosophy based on events and process rather than substance. So do you see that this process worldview as more compatible with quantum theory and possibly with, consciousness studies?
Yes, indeed I do. I think that there's developing in the recent couple of years quite a convergence of some work in consciousness studies and quantum and consciousness there's a number of players that have been looking at this. I'd like to call attention to a recent, at Perry Center in Italy, upon their 25th anniversary, is featuring a preview of a film called Quantum Convergence, The New Science of Consciousness, in the time frame of June 7th to 14th. So I encourage readers to maybe check on the Perry Center. I think it's perrycenter.com, and check out that. It includes a number of scholars discussing those issues. And further, the quantum process, I think, involves both, as I noted, actuality and potentiality. And the consciousness is calling attention to how there's aspects of both. The consciousness, so to speak, by definition, is the anticipatory capability to that which may be versus that which is, and the interplay of that, the self-awareness that's involved with that. And that distinction of actuality and possibility is how one addresses that. And to me, that comes out in quantum physics, in the physics side, and is also comes out with philosophic reflection, including semiotics. Thank you.
Thank you. Thank you so much. And also thank you for the information. Yeah. So maybe I can ask you a second question. Okay. The question is from Dr. Bharat Pandey. He asks, "Sir, actuality means what we can observe and prove, and possibility is about what could be true or discovered in the future. In topics like space plasmas and quantum physics, where many things are still unknown and uncertain, how do scientists balance between what is real today and what might be possible tomorrow? And what do you think new technologies will change this balance in the coming years?"
Well, I think it's always the case we need to apply a more than a little dose of humility with respect to what may be possible in the future. Here I was talking about ontic possibility as a way of thinking about the nature of the real, fully included. But of course, if we think about um, the actualized uh, world we live in, our quantum world, there is a strong epistemic aspect, as emphasized in the previous presentation, about the limitation of problem of knowledge, both now and so forth. But we anticipate, we put together what we do know, and then we have extrapolations and suggestions about what may come in the future through anticipatory functions short term, but maybe predictive capabilities, much of which we need to take with a grain of salt. As for the possibilities of artificial intelligence and quantum longer term, I'm very much a skeptic. That is, mind you, at fundamental information theory, there's both the issue of the syntactic information and semantic information. Syntactic information being that which you can put in a spreadsheet and numbers that you can manipulate, which is often what we think of as information. But there's also semantic information, the aspects of meaning and connection, semiotics, information, fundamentally both. Computers only work with syntactics. They only work with numbers and manipulating them. They only work by an algorithm working with that. So you see the ability to link to the semantic dimension and to make decisions based upon that is not available to computers as presently conceived, including artificial intelligence systems. So in that sense, artificial intelligence is both artificial, strong quotes, and not really intelligent.
Mhm. Yeah, thank you. Thank you for clearing that up. The next question is from Yanugu from ISR Kolkata. He's asking, your use of Vedic cosmology and the reference to Brahma's deep time is very compelling. In your view, is this metaphorical, or do you see meaningful scientific parallels between ancient cosmological frameworks and modern plasma cosmology?
Good question. Well, that's a very good question. I enjoy the raising of that question. And myths are myths. On the one hand, they're not, so to speak, quote, real. On the other hand, they point to realities. They suggest ways of understanding that are with some deep wisdom. And I think that's how we should think of this, that here we have these ancient stories, these ancient mythological representations that have an element of truth, an element of wisdom that we should pay attention to. And Professor Narlikar was very astute in paying attention to how the universe is likely of indefinite age, not of rather short span. And he stuck to that with his steady state cosmology. I think that aspect of his intuition is basically the case. So we can learn from such wisdom, but we need to be skeptical, as we need to be skeptical about any inferences, including ones based upon science in a limited way. So if you focus on science as nothing but, say, dyadic thinking and Boolean logic, we call that's scientism. And scientism is false because science more broadly and the reality more broadly is both the Boolean and the non-Boolean, both dyadic and triadic representation, both the syntactic and the semantic. Uh, so to collapse things to only one among a reductive collapse to only one among these pairings is a basic fallacy that's all too common in contemporary thought. Thank you.
Yeah, wonderful. Thank you. Thank you for the question, Nikhil. Maybe we can ask one more question from Dr. Roshan Tiwari. He says, many of the models that you discussed, like the goal E and non-expansion redshift, offer explanation without relying on dark matter, dark energy, or inflation. What do you think such models remain outside the mainstream despite their explanatory success? Is it inertia, lack of awareness, or deeper philosophical commitments in cosmology?
Well, that's an excellent question, and the suggestions about all of those elements are part of it. deep commitments to careers, to financial investment, to groupthink or contributors, but also just a matter of a typical education. In my field of space plasma physics, I was uh, chagrined to find out that most of the PhDs in my nearby University of Maryland in astrophysics uh, often don't take the plasma courses that are right there from experts in plasma science. And so then they go on and make all kinds of excellent and interesting interpretations of cosmology based upon gravity physics and Einstein's general theory of relativity and so forth. But they'll talk about the gases and astrophysical plasmas, or they'll make other approximations without being aware of the way in which their own domain of application would be affected by considering both gravity and electromagnetism, not just to focus on gravity. And to consider alternative explanations. So there's the tendency to get into a rut in scientific thinking, and this is true in general. I get stuck in ruts, so and I've been caught flat-footed with that. So one needs to be humble on this, and I wish to apply a lot of forgiveness of colleagues that can get a little stuck on dyadic thinking versus a more complex way of approaching these issues. Thank you.
Thank you. Thank you for that wonderful explanation. Maybe we have one more question. Yes, so it's still coming up. Yeah, so Rahul Patel from IIT Bhubaneswar is asking, is our thought, is it like possibilities and it reduces to one of them upon awareness?
Well, that's an interesting question. Yes, I think our self-awareness, our consciousness is, so to speak, a bridge of the uh, order of potentia and actualizations, that we're constantly at this interface. That's our lived experience. The immediate now is that at that interface everywhere. This is the yeah, I think human consciousness is such a pointer to that inevitable linkage of those fundamental realities, both the actual and the possible, and playing out at all times, and that there's different levels of anticipatory capability as developed by Robert Rosen in his work Anticipatory Systems and Complex Systems Theory, that we develop a model of the world, which model incorporates past experience, and that model is a way to, in terms of, say, ducking the ball that comes towards us or something, we unfold the model. So we enfold that experience, we unfold in terms of response. That's how complex systems work. And in that experience leading to the developing the model, then you're constantly in that interface of the possible to the actual. And then when you unfold, it's yet again anticipating, just that which will happen 5 seconds from now or 10 seconds from now, such as averting an accident. As you know, all of us, when we're driving in a car, we're constantly scanning the horizon, constantly scanning back and forth, anticipating what could happen if we don't do things properly. If we turn to the right suddenly and go into the ditch, well, that wouldn't be good. So we then anticipate that, and we then immediately correct. And so that self-awareness, that consciousness, is how we can live successfully live and avert catastrophe through that self-awareness. And so consciousness, in that sense, a fundamental linkage of the possible and the actual, is part of human survival, and thus we would expect to be part of what is filtered out and encouraged in human evolution. Thank you.
Yes, thank you so much. We have more questions, but I think we'll limit ourselves to these many for today, for now, due to time constraint. Thank you so much, Dr. Eastman, for taking your time out, being with us here today, and sharing this wonderful lecture with us. It was really inspiring and amazing to listen to this. Thank you so much.
Thank you for the opportunity. Best wishes upon your golden anniversary.
Thank you. Thank you so much. So with this, we come towards the end of our session today. Before we finish, I would like to remind you about our publication on quantum physics. It's called Quantum Physics and Consciousness, Thoughts of Founding Fathers of Quantum Physics and Other Renowned Scholars. Please try to visit the store.beans.org to get a copy of this. And just a short recap on tomorrow's lecture. We have lecture from Professor David Wallace in the title Many Worlds as a Conservative Reading of Modern Quantum Theory from University of Pittsburgh, USA. Will start at 6:15 Indian Standard Time. So please join us tomorrow for this wonderful session. We look forward to having all of you again tomorrow. So with this, thank you all. See you tomorrow. And for updates, please visit beans.org/quantum lectures, beans.org website, or the store.beans.org. And you can also contact the numbers or email ID in case if you have any queries. Thank you all, and I wish you all have a nice evening.